We're going to continue into Chapter 8, where we're talking about heat and energy. And the next thing we're going to talk about are thermochemical equations, which essentially would be a chemical equation with the energy relationship written as part of it. We'll talk about reverse reactions. So what happens to a reaction if you run it in reverse? What happens to the enthalpy? We're then going to be introduced to what are called standard conditions, and when we are going to be working with tables that are going to tell us the enthalpies of these compounds, well, we need them all under a set of standard conditions. And so standard conditions are their concentrations and their amounts, and we'll talk about what those concentrations are in a minute, but essentially that's what standard conditions refers to. Then we're going to be introduced to what are called standard enthalpies of formation, and this is how the information is tabulated so that we can use it. So when we go to a table, we're going to find that they list what are called standard enthalpies of formation. So we'll learn what they are and how we use them. And then we'll do our normal review when we are done. All right, let's go ahead and get warmed up. Our first question asks, gold has a specific heat of 0.129 joules per gram degree C. When 500 gram piece of gold absorbs 1 kilojoule of heat, what is the change in temperature? Okay, well, we're always going to start with our primary equation when we're using an equation, and our primary equation here is Q equals little m little c delta T, and we're after delta T, so let's isolate delta T. Now Q is the energy, that 1,000 joules. Then little m is the mass of the compound, or mass of the subject, and C is the specific heat. Now remember why I converted kilojoules to joules, because our units of energy are in joules, so don't forget your units. They're still there to help you catch simple mistakes. And if I just put 1 kilojoule on the top and crunched my numbers without taking care of the units, that would have been a simple mistake, but yet a mistake. Okay, if 35 joules is required to heat 50.3 grams of mercury by 5 degrees C, what is the specific heat of mercury? Well, we're going to take that same primary equation and this time solve for C, the specific heat. Do we have Q? Yeah, that's the 35 joules. M is the 50.3 grams, and delta T would be the 5 degrees C. And I come up with 0.139 joules per gram degree C. Now let me ask you, could we ever have a specific heat that's negative? No. Specific heat will always be listed as a positive quantity. Okay, commercial coal packs consist of solid ammonium nitrate and water. Ammonium nitrate absorbs 330 joules of heat per gram dissolved in water, and a coffee cup calorimeter, 4 grams of ammonium nitrate is dissolved in 75 grams of water. Okay, if all the heat is lost to the water, what is the temperature change of the water? All right, our primary, well, we might stop and look and first recognize that the 4 grams of ammonia and the 330 joules of energy per each gram is actually giving us the energy here, the enthalpy change. We see the mass of the water. And so our primary equation, because we're looking at the enthalpy of a reaction, and so Q of the reaction is equal to negative big C of the calorimeter times delta T. Again, remember, if you're dealing with a calorimeter, Q of the reaction is equal to negative Q of the calorimeter. And we don't really have big C. Also, often we're dealing with a coffee cup calorimeter, in which case big C is really the product of the mass of the water and the specific heat of the water that's used. We do have the mass of the water, we do have the specific heat of water, and we have the energy. So let's solve for our change in temperature. Again, the energy of the reaction, 4 grams times 330 joules per gram. Mass of the water, specific heat of the water, and I calculate negative 4.21 degrees C. Now what does that negative mean? That the temperature is going down, and indeed with a cold pack we would expect the temperature of the surroundings, what you have in contact with the cold pack, to go down. Okay, when 2.50 grams of potassium bromide dissolves in 100 grams of water in a calorimeter, the temperature drops from this to that. What is the enthalpy change in kilojoules per mole? So we're after a specific unit when potassium bromide dissolves in water. Okay, well, our primary equation, we're after the enthalpy, and we really only see one equation. The enthalpy of reaction equals the Q of the reaction, and Q of the reaction is equal to negative Q of the calorimeter, and that's where we jump to negative big C of the calorimeter times delta T. Okay, and now we're actually given big C this time. Oh, no, sorry, I'm on the wrong page here. Once again, big C is the product of the mass of the water and the specific heat of water. So mass of the water, that's the heat of water, times the change in temperature. Remember, it's always where you finish minus where you began. If you do it the other way, you're going to have the wrong sign. And I come up with a positive 416.3 joules, and that's going to be per each gram. Now, does our answer make sense? Well, first, it's hard to tell about the size of the number, but the sign is usually easy to tell. Plus, the sign is what's more often going to be where our mistake is. Does it make sense to have a positive quantity? Well, a positive quantity would mean energy in. That would also mean if you're taking energy in, endothermic, the surroundings are going to get colder. So did the surroundings get colder? Yes, indeed, they did. Okay, we're not done because we're after the enthalpy per mole of potassium bromide, and specifically in kilojoules per mole. So step 1 equals kilojoules per mole. Step 2, we're going to take that 416.3 joules, and actually that wasn't per gram, but per 2.50 grams, and convert joules to kilojoules, and convert grams to moles. 1 kilojoule, 10 to the positive third joules, and the molar mass of potassium bromide would be 119.0 grams per mole. And that tells us we would have an enthalpy of 19.8 kilojoules per mole. Okay, chemical reaction in open calorimeter raises the temperature of the calorimeter from this to that without changing the pressure. If the heat capacity of the calorimeter is, calculate the enthalpy change for the reaction. Okay, enthalpy, well, enthalpy of the reaction equals Q of the reaction, which is equal to negative Q of the calorimeter. And negative Q of the calorimeter is negative big C of the calorimeter times delta T. This time we actually are given big C. We have what we need for delta T. And don't forget where you finish minus where you began. And this time I calculate a negative enthalpy of negative 24.6 kilojoules. Now, does that sign make sense? Well, I see that the temperature of the surroundings got warmer, so yes, that does make sense. That does match an exothermic reaction. Like I said, telling this if the size of the number is correct is a bit of a challenge, but telling if the sign is correct, that's usually pretty easy, and as I mentioned, that's also usually where the mistake is. Okay, next one, 5 milliliters of ethyl ether, actually diethyl ether, is burned in the bomb calorimeter. Their temperature rises from this to that. The heat capacity is given. What is the enthalpy change in the units of, actually just specifically per mole of ethyl ether? All right, well, our primary equation, delta H of the reaction equals Q of the reaction. Q of the reaction equals to negative Q of the calorimeter, which is equal to negative big C of the calorimeter times delta T. Once again, we are given big C. Make sure you put your temperatures in the correct order, where you finish minus where you began. And I generate negative 167.5 kilojoules. Does that sign make sense? Is energy being released? Well, if it's getting warmer, energy is being released. And when something burns, indeed, something's going to be getting warmer due to energy being released. Okay, now we were specifically asked for our answer in units per mole. Since we're already in kilojoules, let's make it kilojoules per mole, which by far is the most common unit. Do expect for enthalpy that they're going to be expressed in units of kilojoules per mole. Alright, if I'm after 1 unit per another, I'm starting with 1 unit per another, and that would be the just calculated 167.5 kilojoules over the 5 milliliters. And we already have kilojoules, so we need to just take care of our denominator's unit, so out of milliliters. And using the density term, we're first going to go to grams. Then from grams, we can go to moles. It says 0.714 grams per milliliter, and the molar mass of dialkyl ether is 74.0 grams per each mole. And when I put this on my calculator, I come up with negative 3,472 kilojoules per mole. At first look, I might think that's really a big number, but normally when things burn, there is a lot of energy to be released. Okay, on to thermochemical equations, and a thermochemical equation is essentially a chemical equation. So essentially you'll see a chemical equation written, and then off to the side of that you'll see the energy associated with that reaction. What we're talking about is the enthalpy change for that reaction. So, as an example, here we see how hydrogen and chlorine react to form hydrogen chloride. And off to the side, it gives us the enthalpy change. Delta H is equal to negative 185 kilojoules. And do note per molar quantities. It doesn't say per mole, it says molar quantities. What does that mean? Well, it means based on the way that the reaction is balanced. So that's going to be negative 185 kilojoules per 1 mole of hydrogen reacting, per 1 mole of chlorine reacting, but per 2 moles of the hydrogen chloride formed. Now another way we might interpret this is that negative 185 kilojoules tells us that 185 kilojoules of energy was released when 2 moles of HCl was formed. But it also tells us there was 185 kilojoules more energy stored in the bonds of the hydrogen and the chlorine than in the hydrogen chloride. And hence that extra energy was released. Remember, negative means energy released. And it should totally make sense that the magnitude of delta H, meaning the total amount of energy, is going to be directly proportional to the amount of reactants and products. So if I use 2 moles instead of 1, I'm going to have twice the energy. And if I use 10 moles instead of 1, I'm going to have 10 times the energy. And so again, it should make sense that your enthalpy change is going to be directly proportional to the amount of reactants and products. And here are the conversion factors that we would need to convert between amounts of reactants and products and energy. I think we'll do some examples to illustrate that. Okay, and our first, we're asked to calculate delta H when 1 mole of HCl is formed, and here's that thermochemical equation. And essentially we have what we need, and at this point we're just dealing with an amount different than the 2 moles of HCl, and every time you're dealing with a different amount, I hope you know that means we're reaching for our units. We're after the enthalpy, which is an energy unit, so kilojoules. Step 2, we're looking for a number with a single unit to start with. I hope you recognize that's going to be the 1 mole. Then, step 3, out of moles of HCl, and now can we go straight from moles of HCl to kilojoules of energy? And yes, we sure can. That's negative 185 kilojoules per 2 moles of HCl. And hence just 1 mole would be half of that at negative 92.5 kilojoules. Again, if you're dealing with some other quantities, so they're giving you grams of this or moles of that, expect that you're going to have a step that looks like this. And that we're using our units. Yay, units. Okay, next, calculate delta H when 1 gram of chlorine reacts. Okay, again, we're dealing with different quantities. Hope that rings a bell that we're using our units. Step 1, we're after the enthalpy change, so kilojoules. Step 2, we're looking for a number with a single unit, so the 1 gram of chlorine. And now step 3, nice and easy, let's get out of grams of chlorine. Gotta love the ease of using your units, and if you don't, then you need to practice more. Now, can we go straight from grams of chlorine to kilojoules? No. How are we going to get to kilojoules? From moles. So first in the moles of chlorine, so that we can then go from moles of chlorine to kilojoules. Okay, chlorine, twice chlorine's molar mass, 70.9 grams per mole, and that's still negative 185 kilojoules per each mole of chlorine. And so only 2.61 kilojoules would be released from that 1 gram. Okay, I want to introduce you to what's called the heat of fusion, and this is essentially the heat absorbed, the energy absorbed, when we go from the solid state into the liquid state. So we've got to absorb some energy in order to have us change from that solid to the liquid. Now, I'm not talking about changing temperature, I'm talking about simply doing that phase change. The other one is called heat of vaporization. And this would be the energy required to go from a liquid to a gas. Let me show you through an example. We're told it's found that when an ice cube weighing 24.6 joules, 24.6 grams, melts, it absorbs 8.19 kilojoules of heat. Calculate delta H for this phase change. Okay, well, first I might want to balance that chemical equation, and it does look balanced. Then I'm actually going to be able to use my units for this. I'm after the enthalpy change. And so that would be kilojoules per mole. Again, do expect enthalpy to be in kilojoules per mole. We might be asking the enthalpy for some other amount, but if you're just asked to calculate the enthalpy, it's in kilojoules per mole. Okay, now do note, for step 2, we're looking for a number with a single unit over another number with a single unit, and we have kilojoules. So the 8.19 kilojoules goes on top. And how are we going to go to moles? Well, we actually have the mass. So the 24.6 grams of water goes on the bottom, and it looks like we only need to take care of our denominator, so out of grams of water, and yes, we sure can go to moles. There's your most common calculation in all of chemistry, going back and forth between grams and moles. And the molar mass, 18.0 grams per each mole, and when I put this on my calculator, I come up with 5.99 kilojoules per mole. And note how I was able to complete the thermochemical equation by writing delta H equals. Okay, on to reverse reactions, and what's going to happen when you take a reaction and flip it around so it goes the other way? Well, I hope that you already can interpret or assume that that means that we're going to have the same magnitude for your change in enthalpy. It's just going to be opposite in sign. Now, I hope you came to that conclusion based on such a simple thing as recognizing if I'm going the forward direction and I'm taking 3 minus 5, I get negative 2. If I go in the reverse direction, I take 5 and subtract 3, and I get negative 2. So remember, if you take two numbers and make one negative and the other one positive, and add them together, you'll get the exact same number, just a different sign, as if you switch those signs. So again, I hope that it makes sense that our enthalpy would be equal in magnitude, but opposite in sign. So here, if we have water in the solid state going to water in the liquid state, and we have a positive 6 kilojoules per molar quantities, then if we went the other way, from water in the liquid state to water in the solid state, we're going to release that 6 kilojoules. Because again, you're taking what's on the right and subtracting what's on the left. meaning the enthalpy stored in the bonds on the products minus the enthalpy of the bonds stored in the reactants. So again, I hope it totally makes sense that it's the same number, but opposite in sign. So again, equal in magnitude, but opposite in sign. Let me introduce you to Heth's law, which is similar to the state property, but essentially he went a little further and just simply said that if you have a reaction that can take place in multiple steps, then the overall reaction would be the sum of those steps. Now what that means is if we can take multiple chemical equations and add them together, then the enthalpy change will be the sum of those individual enthalpies. So again, if your overall equation is equal to multiple steps, so think of equation 1 as the first step, equation 2 is the second step, etc., then the enthalpy of that reaction will be the sum of the enthalpies of those steps. And that's going to allow us to add chemical reactions together. And because of that, sometimes that means we can calculate the enthalpy of reactions that we can't actually measure directly. Okay, let's see some examples of what we might do with this. We're asked to calculate delta H for the reaction where carbon reacts with oxygen to form carbon monoxide. And we're asked to do so from the known enthalpies of carbon reacting with oxygen to form carbon dioxide and carbon monoxide reacting with oxygen to form carbon dioxide. Okay, where do we begin? Okay, just for discussionary purposes, our first equation is our main equation we're trying to get. Those other two equations, let me call them equation 1 and 2. So equation 1, carbon plus O2 goes to CO2. First, let's start with, and this is what we would always do when we're adding chemical equations together, and there's going to be many instances where we're adding chemical equations together, and they always start the same way. First, let's identify for each of the reactions, do they run in the correct direction, or do we need to reverse it? So let me look at that first equation. Is this running in the correct direction, or should I reverse it? Well, I see carbon and oxygen on the left, and there is no CO2, so let me forget about the CO2. Carbon and oxygen on the left, and I need them on the left. When I look at my main equation, they're on the left, so that means I'm going to use equation 1 as written. I might have to multiply by some coefficient, but it's at least ran in the correct direction. Now let's look at equation 2. And I see carbon monoxide on the left, and I need carbon monoxide on the right. I'm not going to worry about the CO2. Remember, it's not even part of the reaction. And I've already am dealing with oxygen, so do try to just grab onto somebody that is part of the equation, and at this point I'm grabbing CO. And I need it on the right. So what do I need to do with equation 2? I need to invert it. Put your thumb over that half right now. Okay, so that half would then be for the next step. The next step is, do I need to multiply either of these equations by some coefficient? And we realize we need 1 CO2, not 2, so that should make it pretty easy to recognize we need to multiply that second equation by 1/2. Now, what happens if we multiply the equation by 1/2? We'll know what happened to the enthalpy. It was also multiplied by that 1/2. Now, when I add those two equations together, I get my main equation, the one I came for, and do note, then I just add those two enthalpies together. I've already identified the signs, I've already identified their magnitude. Okay, I want to introduce you to standard conditions. When we go to tables to get information for enthalpy, and we'll be doing a lot of that in just a little bit, and a lot in our future. If you're tabulating something, we need essentially them all to be at some set standard conditions. So what are their concentrations, what are their amounts, etc. Because if you change your amounts, you would change your enthalpies. If you change your concentrations, we really haven't even talked about concentrations. Concentrations is kind of like an amount. That also is going to be part of this. And so our standard conditions turn out that for anybody in their pure state, we would have 1 mole quantities. If you happen to be in a mixture, meaning you have a variable concentration, then we would use your concentration, so your concentration will become part of it. And again, our standard concentration then turns out to be 1 mole per liter for solutes in solution, and 1 atmosphere for substances in the gaseous state. So again, our standard conditions would be 1 mole for anybody in their pure form, so solid or liquid, and then 1 molar concentrations for anybody in the aqueous state, and then 1 atmosphere for anybody in the gaseous state. So just keep in mind, those are our special conditions, and they're only special in that we needed somebody. I hope that's obvious. All right, we'll be using a lot of that in a little bit. Let me kind of get a little further, and then we'll see where those tables come in. And this is for standard enthalpies of formation, abbreviated delta H naught sub F. And sometimes we call those standard conditions naught. So if in a normal reaction, we're after delta H naught. So again, when we have that superscript of 0, we call it naught. Okay, so this is delta H naught of formation, sometimes called the standard heats of formation. And ultimately what this is the formation of a compound from its elements and their most stable state. So note here in this example, we have aluminum oxide being formed from its elements, aluminum and oxygen, and their most stable states. So aluminum is going to be a solid, and the oxygen is going to be a gas. Since we're dealing with standard conditions, that gas is going to be at 1 atmosphere of pressure. And so we have delta H for the reaction is written here. But if it's at standard conditions, which it is, then that's also delta H naught. And if we're forming a compound from its elements, then it's delta H naught sub F, delta. So essentially the standard heat of formation. Now, the standard heats of formation are tabulated in table, I think it's 8.3, and we're going to be using those quite a bit when we're making calculations of what is the enthalpy of this reaction. Now, I do need to mention, as you see right here, that when it comes to any element in its most stable state, its enthalpy of formation is 0, because think of it, you're forming it from itself, and there would be no change. So that's going to simplify a lot of our calculations, but we need to recognize that immediately. Anybody in their elemental state essentially would have a value of 0 for their standard heat of formation. So that means we normally omit them from our calculation. Now the calculation for our enthalpy change, delta H naught, the number 1 calculation that we perform based on this chapter, delta H naught, our standard enthalpy of reaction, would be, and remember this is a state property, so where it's where you finish minus where you began. So it's going to be the sum of the heats of formation in the products minus the sum of heats of formation in the reactants. And I would remind you that that capital epsilon is used to refer to the sum of. So again, delta H naught of the reaction is equal to the sum of the heats of formation in the products minus the sum of the heats of formation in the reactants. Let's practice. All right, we're asked to express the standard enthalpy change for this reaction, and we're asked to do so using table 8.3. So that's a way of saying you need to calculate the enthalpy of this reaction based on that tabulated data. Okay, first, we have a calculation before us, and this time let's go all the way to the beginning. We've got a calculation before us. We have 1 and 2 possible tools, equations or units, and most of this we've been using equations, and sure enough we have an equation. Our primary equation, the one that's going to get us the answer we're after, is delta H naught of the reaction equals sum of the heats of formation in the products minus sum of the heats of formation in the reactants. Well, I'm really just looking at the heat of formation of the 1 aluminum oxide minus the heat of formation of the 1 iron 3 oxide. What happened to the iron and the aluminum? Remember, their standard heat of formation would be 0. Any element in its most standard state, its most stable state, is going to have a standard heat of formation of 0. That should make a lot of sense since it's where you finish minus where you began. And there's just one of these. If there was 2, we'd have to take that into account. So don't forget, those coefficients are now going to show up. And so we add 1 mole of aluminum oxide at a negative 1675.7 kilojoules per mole, minus the heat of formation of 1 iron 3 oxide at a negative 824.2 kilojoules per mole. Putting this on my calculator, I come up with negative 851.5 kilojoules. And I don't want to just leave it as moles, I want to leave it as per molar quantities because it is per 2 moles of iron being formed. Okay, real quick, do you always have to write down all this information? No, you probably want to just skip down to delta H naught equals, and you might want to just get into delta H naught formation of aluminum oxide minus delta H naught formation of the iron 3 oxide. In other words, you probably would skip that first line. But since you're going to be showing your work, you do want to include that second and third line in addition to your answer. Okay, similar questions, same approach. Calculating enthalpy from the table. It's the sum of the heats of formation in the product, so that's going to be the 2 aluminum ions, minus the sum of the heats of formation in the reactants, that's going to be the 3 copper 2 ions. And remember, if you're in your elemental state, you don't show up in this calculation because your enthalpy formation will be 0. But this also shows that if you're in an ionic state, you don't have a 0. So the copper 2 ion and the aluminum ion are not going to be 0. The elements would be, but their ions are not. So hopefully you won't make that mistake. The elements have a value of 0, but the ions do not. And this time we have 2 aluminums, note how that shows up, and 3 coppers, so note how that shows up. Putting this all on my calculator, I come up with a negative 1256.4 kilojoules per molar quantities, which means based on the way the chemical reaction is written. Okay, let's practice some of the things that we have just learned. First, which of the following statements are true? So, true or false, Hess's law states that delta H for an overall reaction is the sum of the delta H's for the individual equations. And that is true. True or false, the molar enthalpy of formation of a compound is equal to the enthalpy change when 1 mole of compound is formed from its elements. That's almost a definition of enthalpy of formation, so true. True or false, a reaction with a negative enthalpy is exothermic, and that's true. Remember, negative means energy is being released, and release means exo, energy out. True or false, the enthalpy of formation of an element in its most stable state is equal to 0. True. That simplifies our calculations a lot. And true or false, the sum of the enthalpies of formation of the products in a chemical reaction is defined as the enthalpy of reaction. No, it's the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. So E is false. Okay, we're told hydrazine is a liquid used as a rocket fuel. You may be familiar with it. And it reacts with oxygen to yield nitrogen gas and water. And I would point out the formation of nitrogen is often very explosive, and hydrazine can actually be explosive. Okay, anyway, the reaction 3.60 grams of hydrazine involves this amount of energy. Calculate the enthalpy change per mole of hydrazine for the above reaction. Okay, now, are we going to be, well, first, do we have a balanced equation? Yes, so I can't think of any preliminary steps. Then, what are we doing here? Are we using an equation or are we using our units? I think I'm using my units, so I'm going to go ahead and take a try at that. And if I find that doesn't work, that will tell me I'm wrong. I'm after the enthalpy change, so kilojoules per mole. And I know for step 2 then, if I'm finishing with 1 unit over another, then I'm starting with 1 unit over another. Alright, I've got grams of hydrazine and kilojoules of heat, which is going to go on the top and take us to kilojoules. Well, of course, that's the kilojoules. Now, where'd that negative come from? We're told that it's evolved, it's released, so that tells us that it was negative. And you'd have to put that 3.60 grams on the bottom. So I hope we have no problem with step 1 and step 2, and I'm sure if we were this far, we can see the rest of it falling into our lap. Step 3, let's get out of grams. Can we go to moles? We sure can. So it looks like that's all we really needed. And I come up with negative 620 kilojoules per mole, and that makes sense. Okay, methane, CH4 is methane, reacts with oxygen to produce carbon dioxide, water, and heat. And now we're asked what is the value of delta H if 5 grams of methane is combusted. Do note, in addition, they give us the thermochemical equation, which gives us the energy change that we need. Okay, now, what is the value of delta H for another amount of methane besides the 1 mole that's reacting? So I hope that it jumps out at us. We're going to be using our units. So step 1, we're looking for an energy unit. Kilojoules is by far the one that we want to use. Step 2, that 5 grams of methane is the only number really given up there. Remember that kilojoules is actually a conversion factor because it's per molar quantities. So, step 1, step 2, on to step 3. Let's get out of grams of methane. Here comes the big question. Can I go straight from grams of methane to kilojoules of energy? No. How am I going to get the kilojoules? From moles. So first from moles of methane, and then from moles of methane to kilojoules. I hope you have no problem determining the molar mass of methane at 16.0 grams per each mole. And that delta H equals is telling us negative 890.3 kilojoules per 1 mole of methane reacting. For negative 278 kilojoules. Does our answer make sense? Well, I definitely expect a negative when something is burning or releasing energy. Okay, acetylene, C2H2, is a gas commonly used in welding. If this mass of a sample is combusted in a bomb calorimeter, the temperature rises this much. If the heat capacity is this, determine the enthalpy change per mole of acetylene. Okay. Where are we? Well, first, are there any preliminary steps? It's not coming to me, so I'm going to say no. Then equations or units, and most of these types of problems have been actually an equation. I'd be using my units if I have some way to just go ahead and get the kilojoules and get to moles, but that's not what's going on here. So, what's my primary equation? We're after the enthalpy change. So, delta H equals Q of the reaction. So enthalpy of the reaction equals Q of the reaction, meaning the heat of the reaction, which is equal to negative Q of the calorimeter, which we remember is negative big C of the calorimeter times delta T. And they do give us big C. They do give us delta T. And let's see, the calorimeter increased in temperature by 16.43 degrees C, so our delta T was positive. What if the calorimeter temperature decreased by 16.43 degrees C? Well, then it would be a negative 16.43 degrees C. And that tells me that I have an enthalpy change of negative 116 kilojoules, and do note that's per the sample size, 2.328 grams of the acetylene. I hope that you recognize and expect the next thing is to use our units to convert that into the enthalpy per mole of acetylene. Okay, that's going to carry units of kilojoules per mole. We're going to start with the just calculated kilojoules per 2.328 grams of acetylene. We already have our numerator, so let's take care of our denominator. And can we go from grams of acetylene to moles? There's our most common calculation again. And for acetylene, twice 12 plus twice 1, or 26 grams per mole. I then come up with negative 1,300 kilojoules per mole. And again, for things that are burning, I would expect fairly high values for their enthalpy, meaning enthalpy of the reaction. Okay, determine the heat of reaction for the decomposition of 1 mole of benzene to acetylene. So that C6H6 is benzene, the C2H2 is the acetylene. And we're asked to do so given the following thermochemical equations. So what's going on here? Well, if you're given multiple equations, expect that you're adding those equations together. So, again, the equation at the top, that's our main equation, the one we're after. The two below, we're going to call that 1 and 2. And just like we did before, let's start with equation 1. Do we write it in the forward direction? Well, let's look for benzene or acetylene in that equation, and there's just benzene, and it's on the left. And where do I need benzene? On the left. So equation 1 is written as is. Then what about equation 2? Well, where's benzene and acetylene here? Well, there's only acetylene, and acetylene is on the left. Where does acetylene need to be? On the right. So what are we doing with equation 2? We're inverting equation 2. So note I just flipped it around. Now, do I need to multiply either of these chemical equations by some constant, some coefficient, to essentially get my desired equation? Well, I'm going to go back to what I really need. I need how many benzenes? 2. There's going to be 1. In the equation, there's 2. So how do I get from 2 to 1? Multiply that whole equation by 1/2. Know what happens then to your enthalpy. It's also going to be multiplied by 1/2. Okay, on to equation 2. And first, do note my inverting it went from being negative to positive. And now, where's that acetylene again? Oh, there it is, C2H2, and there's 2 of them. How many do I need? I need 3 of them. I've already identified they're on the right, but I need 3, not 2. So how do I get 2 up to 3? I'm multiplying the whole equation by 3/2. And again, do note, I'm going to multiply my enthalpy for the reaction by 3/2. Now, when I go to add them together, sure enough, all of those oxygens and all those carbon dioxides and waters cancel to leave me simply 1 benzene goes to 3 acetylene, and here's the enthalpy change, a positive 631 kilojoules. Does our answer make sense? Should it be positive? Well, this time it's not really easy to predict. So at this point, I really don't have a lot to go on. So I'm just going to say it seems reasonable, and hope I haven't made some simple mistake that's given me a close but a wrong answer. Again, the close but wrong answers we're not going to get. The ones that are obviously wrong, those are the ones we're after. Remember, critical thinking begins by asking, does this make sense? I would also point out, when we were doing this, I wasn't looking at the oxygens, I wasn't looking at the carbon dioxides, I wasn't looking at the waters. They weren't part of the original equation. So I was just concentrating on benzene and acetylene. And I recommend you do so too. Okay, next, in which the following below is, in which the reactions below is delta H, an enthalpy of formation. So what does that mean to be an enthalpy of formation? Enthalpy of formation is where you are forming a compound from its elements. So there's 2 things we really need to look at. We're forming it from its elements, and there's always just 1 of that compound. So in this first example, there's 2 carbon monoxides produced, so that's why this is not going to be an enthalpy of formation. It's always to form 1. Here we see 1 compound formed from its elements, so that would be an enthalpy of formation. Here we see one compound formed from its elements. So again, that is an enthalpy of formation. And here, again, I see one compound formed from its elements. So we have an enthalpy of formation. What about here? There isn't just one. So that's not an enthalpy of formation. And what about here? The calcium hydroxide is not being formed from its elements, so that also would not be an enthalpy of formation. And here, again, 2 perchloric acids. If it was 1, it would be, but for 2, it's not. And what about this one? Yes, 1 compound formed from its elements. And here, no, you're forming 2 compounds. And we're also not forming them from their elements. Okay, determine the heat of formation of sulfuric acid from the following thermochemical equations. Okay, so again, multiple equations, we know we're adding them together, but where's our main equation? Where is it? Where is it? Oh, we weren't given the main equation. We're going to have to build it ourselves. So, we're looking at the heat of formation of sulfuric acid, H2SO4. Okay, so we know we're forming sulfuric acid, H2SO4. Looks like we have some hydrogens, some sulfurs, and some oxygens that are going to form it. So again, we're going to form this compound from its elements. Now, I'm going to just kill some time and balance it all at once. If you have any difficulty with this, well, then I would have started with, well, I think I would have started with sulfur, 8 on the left, so I need 8 on the right. That then tells me 16 hydrogens, so 16 on the left, 16 on the right. And 8 times 4, 32 oxygens, 32 on the right, 32 on the left. And so I hope you can see that this is balanced. All right. Now, on to adding our chemical equations together. Now, let's look at equation 1. And am I looking at the oxygens and the sulfur dioxide? Well, actually, I'm looking at the sulfur here. To some extent, I'm also looking at oxygen. But I see a couple of reactions in there with oxygen. So that's why I'm going to concentrate on the sulfur. And I would also the SO2, but there's no SO2 as part of my reaction. So note what I just said. I'm not really looking at the oxygen. Why? Because in equation 2, equation 4, they also have oxygens. So they may be the one that's going to be where I need it. So the sulfurs is what I'm looking at. But as I'm looking at it, look at the one below it. Both of them have sulfurs. Let me go ahead and spill the beans here. One of these is not needed. Which is needed and what's not needed? So equation 1, where sulfur and oxygen form sulfur dioxide, is that needed? Or equation 2, where sulfur and oxygen react to form sulfur trioxide. One of those is needed. I'm not going to use both. So which one is needed? I'll give you a moment to think about this. So which one is needed? Yeah, we're going to use a little logic here. Well, do note, we're forming sulfur trioxide or sulfur dioxide, and they're not part of the reaction. So what does that mean? That means they need to cancel. One of those I can cancel with somebody else, the other one I can't. Does anybody else have sulfur dioxide in it? No. That's why sulfur dioxide, equation 1 where sulfur dioxide is formed, is not going to be part of this at all. Note how in equation 2 and in equation 3 we have sulfur trioxide, which means we have the chance for it to cancel. Okay, so let's go ahead and break out equation 2 and use it as written. Again, so the sulfurs are on the left. Then equation 3, and sulfuric acid is the only one that's part of my original reaction, and I need it on the right. So I'm also going to use equation 3 as written. What about equation 4? Well, so far nobody's had hydrogen, and so hydrogen's on the left here, and I need it on the left, so it looks like equation 4 is also used as written. Okay, so for equation 1, do I multiply that by any coefficient? Well, I need just one octasulfur. So no, I'm going to just multiply that by 1. I need 1. What about equation 2? Well, what about the sulfuric acid? Again, look at the guy that's part of your reaction. Sulfuric acid is there's only one of them, and I need 8 of them. So again, when I look at my main equation, I have 8. When I look at equation, I guess that's 3, I have 1. So I'm multiplying equation 3 by 8. And I hope you're okay with me calling that equation 3, just following from above. 1, 2, 3, 4. This is equation 3. Then equation 4, let's see, what are we doing here? Well, remember, we were banking on this guy for the hydrogens, and I need how many H2s? 8. Since in this equation there's 2, I'm multiplying this equation by 4. Now, you can always write everything out if you're having a hard time seeing it, but you might recognize that all of those sulfur trioxides canceled. And water's canceled. And then when I'm left, I have my desired equation. And note, we used equation 2 as written. Equation 3 we multiplied by 8. Equation 4 we multiplied by 4. Don't forget to come back and put those numbers in when you're actually crunching them to get your final enthalpy. Now, that's the enthalpy of the reaction as we wrote and balanced it. Why might I need to take this additional step? Well, remember, we're after the heat of formation. So that means just one sulfuric acid. So that's why we multiply the whole equation by 1/8. And I hope you can see now all those coefficients are divided by 8, and the enthalpy change has been divided by 8. Okay, we're asked to use molar enthalpies of formation to determine the heat of combustion of 1 mole of glucose. Well, we have talked before about combustion, and combustion is where we would take an organic energy storage molecule like glucose, then react it with oxygen to form carbon dioxide and water. All combustion reactions are some organic fuel plus O2 goes to CO2 and H2O. And now, let's go ahead and balance it, and I'm going to let oxygen for last, starting with carbons, 6 on the left, let's put 6 on the right. Then hydrogens, 12 on the left, let's put 12 on the right. Let's now count oxygens. So I have 6 times 2 for 12 from the carbon dioxide. Another 6 from water. 12 and 6 is 18 oxygens on the right. Now I might be tempted to divide that by 2 to get 9 O2s. Why is it 6? But look at the glucose. It already had 6. So we only needed 12, not 18, for 6 O2s. All right, my equation's balanced. Now for the enthalpy of the reaction, it's already written for the correct combustion reaction. And so we're looking at the sum of the heats of formation in the products minus the sum of the heats of formation in the reactants. So we're looking at the heat of formation of the 6 carbon dioxides and the 6 waters minus the heat of formation of the 1 glucose. What happened to the oxygen? It's in its elemental state, which means it's 0, and hence falls out of the equation. Let me crunch those, bring out those numbers. So 6 times the enthalpy for the carbon dioxide, 6 waters times the enthalpy stored in the bonds of the water, minus 1 glucose, for negative 2802.5 kilojoules per molar quantities. Does our answer make sense? Well, do note that's a lot of energy to be released, and that's what an energy storage molecule is there for, to store all these energy so it can be released when we need it. And that's essentially what fuels all of us, glucose. Okay, the molar enthalpy of formation of water in a liquid state and water in a gaseous state are given. And now how much heat is released when 25 grams of water condenses from the gas to the liquid phase. Now, it may be helpful to write out that reaction. So water in a gas going to water in a liquid. 1-to-1 reaction. We put those ones in. And now, the enthalpy of the reaction is going to be equal to the sum of the heats of formation of the products, which is the energy stored in the product bonds, minus the heat of formation of the reactants. And remember, enthalpy is the energy stored in their bonds. We're looking at the energy in the product bonds minus energy in the reactant bonds. So we're looking at the heat of formation of water in the liquid state minus the heat of formation of water in the gaseous state. Let's bring out those numbers. Now before I hit my equal sign, or go on to the next, to produce that for you, I want you to come up with your own answer in terms of the sign. What is this going to be? Is this going to be positive or is this going to be negative? So when water goes from a gas to a liquid, what happened to the surroundings? Did the surroundings get cooler or hotter? Did it release energy or did it absorb energy? Well, going from a liquid to a gas absorbs energy, so going from a gas to a liquid must be releasing that energy. And so when we come up with a negative enthalpy change, I hope that this makes sense to you and that this is what you predicted. Okay, so there's our enthalpy based on the reaction in molar quantities. We're asked for the heat involved when 25 grams of water is undergoes this process. So this isn't the same quantities. We're dealing with different quantities. What are we doing now? And I hope that you know that means we're using our units to get to our final answer. We're after this new enthalpy, so we're still after kilojoules. This time it's for 25 grams of water. So I hope step 1 and step 2 just fell into your lap, as does the beginning of step 3. And now, can I go straight from grams of water to kilojoules of energy? No. How do I get to kilojoules of energy from moles of water? So first in the moles of water, so that I can go from moles of water to kilojoules. Molar mass of water, 16.0 and twice 1.0 for 18.0 grams per mole. And that was negative 44.0 kilojoules per each mole of water. And that comes out at negative 61.1 kilojoules. A little bit more than a mole, so a little bit more than the 44 kilojoules. So far, everything here makes sense. And I hope that you're regularly looking through your work to see what you're generating for answers. Does this make sense? Okay, that concludes this lecture where we went a little further into thermochemistry. We learned what a thermochemical equation is. Simply, it's a chemical equation where off to the right it says delta H equals. So essentially talking about the energy change. And again, we're talking about energy changes. We're talking about the difference in energy stored in the bonds of the products minus the bonds of the reactants. Remember, all this energy is energy that's stored in chemical bonds. Reverse reactions. What did we learn about reverse reactions? That writing a reaction in the reverse direction, you're going to have an enthalpy that is equal in magnitude, but opposite in sign. So again, same size number, just different sign. And that should make sense just from what we know about math. Then standard conditions. And standard conditions are where we have 1 mole for species that are in their pure state, and then 1 mole per liter for species in solution, and 1 atmosphere for species in the gaseous state. And then lastly, we learned about standard enthalpies of formation. And standard enthalpies of formation is really, well, essentially it's the formation of a compound from its elements in their most stable state. But the thing is when we come to the tabulated values of enthalpies, they're all going to be tabulated as delta H naught sub F. So as you just saw earlier, we reach for that table to do a lot of these calculations. Okay, that concludes this lecture.